So, in the last class, we discussed about feedback amplifiers, where we have we had this basic amplifier. It's an open loop amplifier, and let me label this with A. And the general feedback network was something like this, where we are trying to sample the output V naught, or basically it can be written in general as X naught, right? And the signal source to the feedback amplifier is written as XS, and there is a beta or the feedback network that samples the output signal X naught and splits out a signal which is XF, and that has been mixed across the input. Okay, so this is the type of network that we had, and this basic amplifier we had discussed about four different types of amplifiers that we can fix here. So we had discussed about this voltage amplifier, and then later we discussed about the current amplifier, and then transconductance amplifier, and the third is the trans resistance amplifier. Yeah. So in the previous case, or in the previous stream, I have said that all these structures that we have uh, taken and fixed onto this basic amplifier was considered to be an ideal structure, or the ideal model of these amplifiers were being used on it. Okay, and whereas uh, so let me write this. So all the basic amplifiers were considered as an ideal model, and then we had some non-idealities across the network, across the sources. So sources, in the sense I'm talking about the input source as well as the output load. So sources and load, they were taken as non-ideal cases. So which means that if I have a voltage input source or input signal source, so that will have a resistance Rs. Okay, so this finite amount of resistance is considered to be a non-ideal source, and if it is a current input source, then we had taken this Rs in series. Okay, so as a Norton equivalent circuit, we have taken as a parallel combination with the current component I. Okay, so these were considered as the non-ideal models, and we fixed these non-ideal models to this ideal model of this basic amplifier. And even for the feedback network, even though it was not specifically said, but these feedback networks, when they are built by making use of resistive loads, okay, they tend to form a loading effect. Okay, so they basically tend to load this basic amplifier. Okay, so both across the input as well as across the output. And today we'll discuss about this loading effect, specifically on the non-ideal model of this basic amplifier. But these loading effect will not have any impact, or these are non-ideal characteristics of resistances that we have across the input sources, and even the load, even the RL, will not have any impact on this basic amplifier if this basic amplifier is built using this ideal model. Okay, so let us try to prove that with a set of example. But this is the conclusion that we have derived in the last previous session, and we have used all these non-ideal characteristics of the feedback, or non-ideal model of the feedback network, as well as we use the non-ideal model for the sources and the loads, and but except for the basic amplifier, which we took it as ideal model. Okay, so now in today's class, our major focus would be on this voltage amplifier, and let me start the discussion with two kind of cases. Let me write it as a voltage amplifier with feedback. Okay, and so the discussion of this particular amplifier with feedback will fall into two categories, and all other type of amplifiers that we are about to discuss will also have two kind of cases. The first case being the taking the non-ideal model of the basic amplifier. So whenever I say basic amplifier, I am talking about the open loop amplifier. Okay, so we'll take this non-ideal model, but to this non-ideal basic amplifier, we'll just try to add at the first stage the ideal model of sources and the load as well as the feedback network. Okay, so we'll just take all those non-ideal models of these things, and then we'll try to add upon to this. Okay, and in a way we'll try to see there are two things that could be evaluated out of this discussion. The first being the input and output impedances of these basic amplifier will basically have some changes. Okay, so the input and the output impedances of the closed loop amplifier or the feedback amplifier will certainly have some sort of changes in their values. Okay, so that is a first type of concept that we will learn in this first case, and we will also try to discuss about what type of yeah, so not over here, yeah. So in the second case where we will be considering again the non-ideal model of the basic amplifier, but to this what we do is that we will just try to add upon the non-ideal model of all these sources, loads and the feedback network. Okay, so during this discussion we'll be uh, trying to learn some new concepts, which is basically the feedback network model. Okay, so we'll just try to address the feedback network model, which is a two-port. What type of two-port network or the parameter model can be used? Okay, so basically, we'll try to study about those feedback networks, a non-ideal model, and the such non-ideal model can be characterized by a particular two-port network model. And as you would have already learned about a few models, which I'll just list it out, but specifically for today we'll just use only one specific model among those four two-port models that is available. Okay, the first one being the hybrid model or H parameter model. Okay. The second one is the Z parameter two-port model, and the fourth one is the Y parameter model, and fourth one is G or the conductance parameter model. I guess these are the models that we will be using. I guess G, yeah, I'm not pretty sure about this. Yeah, so these are the different two-port models that would uh, be used in order to model the non-ideal model of the feedback network. Okay, so we'll be using these things, and for today, when we discuss about this voltage amplifier, we'll be picking one among those four two-port parameter model. Okay, so we'll talk about this, which parameter better suits for our voltage mixing, voltage sampling, feedback topology. Okay, so we'll just discuss upon it, and then we'll just choose one among those four, and then we'll utilize that for the discussion. Okay, so let me begin with the first case where I'll be considering the non-ideal basic amplifier, and whereas the other type of network that or the components that are associated with this feedback network will have this ideal structure in them. Okay. So So let me just begin with just one. I'll write it as ideal case, where the ideal case is not ideal with respect to the basic amplifier, but it is ideal with respect to the sources and the feedback factor. Okay, yeah. So having written this, let us try to bring our model. And as I said, let me just first begin with the discussion of the basic amplifier of a voltage amplifier, the basic model of a voltage amplifier. Okay. And if it is an ideal model, then what I said is that it will have an input impedance which is infinite. Okay, so basically this will have an input impedance which I write it as Ri for the basic amplifier. Okay, so that would be considered as infinity, and whatever the voltage that we have will be taken as Vi, and then we'll have something known as voltage controlled voltage source. So in this case it would be the gain times, so let me write this gain as mu times that of Vi, and it's this mu times Vi is nothing but our voltage controlled voltage source, and this is the model that we had as an ideal model. Okay, where the output impedance associated with this model will have Ro, which is 0 in this case. So clearly I have used few letters here, so please try to look across this. The Ri and R naught are the input and output impedances or the resistances of the basic amplifier or the open loop amplifier. Okay, so we'll be having different other notations as well throughout the discussion. And now that I just want to bring in the non-ideal behavior into this particular model. So in that case, let us try to talk with respect to the input port of this basic amplifier. So having a non-ideal model means that the input resistance Ri is no more an infinite value. So rather what we have is a kind of resistance. Let me write it as non-ideal model, and the input impedance is no more infinity, but rather it's a finite value, and the value of it is given as Ri. And again one could model this plus and minus, which is a voltage controlled voltage source with mu times that of Vi, and as I said, even the output impedance, if it is a non-ideal model, will have a finite value of it. Okay, so which I label it as R naught in this case, and the input to this basic amplifier is always Vi, and the output of this basic amplifier will be a Vo. Clear? So this is the non-ideal model. So now that we'll use this non-ideal model of the basic amplifier, put them into a feedback network where the source signal as well as the feedback network will be an ideal network. Okay, so let me do the same. So this is my closed loop amplifier, or in short I will call it as a feedback amplifier. Okay, and one more important thing is that the gain of this particular quantity, which is the basic amplifier, the gain of basic amplifier, let me write that. Amplifier is defined as capital letter A, and which is nothing but the ratio of V naught by Vi, and that could be in this case is written as mu. Okay, so as of now we have this as our quantity, and now that we just draw the model of the closed loop amplifier for a voltage amplifier, where the input source, as I mentioned, supposed to be a voltage source, and it's an ideal, means that there won't be any series resistance or the source resistance Rs. So the source resistance Rs would be completely equal to 0 whenever I say that the source signal is ideal. Okay, so in that case we haven't added the source resistance Rs in this case, and this has to be connected to the basic amplifier. So the inside this basic voltage amplifier, what we have is a resistance which models the non-ideal behavior of the voltage amplifier, and also it will have a gain which could be written as let me use it as mu times that of Vi, and the Vi is nothing but the input port or the voltage drop across this input port of the basic amplifier, okay. And it will also have the resistance R naught along with it, okay. So this entire part comprises our basic amplifier, and the output of this basic amplifier will be a voltage which is V naught. So hope that it is clear, where the yellow dotted line specifies the basic amplifier model, which is modeled non-ideal, which models the non-ideal cara of this, okay. So now that we need a feedback network, let me draw the feedback network with just the dotted line, but let us try to recall how it can sample the voltage, okay. So basically, in order to sample the voltage, what we wanted to do, yeah, is that we have to use the shunt connection. So it is something like a voltmeter where you tap the voltage by measuring the or by using the probe across both these wires, right, and then feed them as an input to this beta network, and the input of this feedback network will be always this V naught, okay. So this is what we are trying to feed through this feedback network, and later we'll just try to model how it has to be done. And I also have to say that the load of this voltmeter or of this voltage amplifier basically has to be an ideal one. So which means that the load impedance RL, if at all, if it is an ideal, supposed to be an infinite, okay. So it should not have any drop across it, clear. So clearly, what I really mean here is that if at all, if there is a finite amount of resistance RL, then the R naught in combination with this RL will create a voltage drop across this particular point, okay. So the value that I would get at this particular node will not be equal to V naught, but rather it's a kind of voltage division rule that has to be applied in order to measure that particular voltage, okay. So since in this case we are going to discuss about the non-ideal model of the source signal as well as the load, I am just going to assume that this load has infinite output impedance such that I can bring out this V naught as it is to the output, okay. Yeah. So now let me try to finish this circuit of the feedback network. Now we also know that the output of this will have a voltage which is Vf, and this voltage has to be added in series, right. The connection that I need to make in order to add supposed to be a series such that the summation of this Vi and Vf should sum up to a value of the source voltage which is Vs. So I have to add them in series, so due to which I have this feedback network output connected in series with the input, okay. So this is something known as a series mixing here, okay, and at the output we have a shunt connection, at the input we have a series connection. So now that let us try to fill in this. So as we know that this network has to read in this V naught, and I need some sort of element which will try to read this V naught and convert in terms of a voltage. So again, what we could model here is something like a voltage controlled voltage source, okay. So however we had a voltage controlled voltage source for the basic amplifier, we also have the same similar voltage controlled voltage network for the feedback amplifier, okay. I hope that it is clear. So the one that I have drawn here is nothing but the beta network or the beta or the feedback circuit, okay. And in this case I am just going to add few more quantities or the parameters which will be using it later. So I am just going to call the input impedance as RIF, and RIF is nothing but the input impedance of a feedback amplifier. Okay. This is known as input impedance of the feedback amplifier, okay, or the closed loop amplifier. And I'm just going to observe this output as ROF, which is again termed as the output impedance of the feedback amplifier. Okay. So now this is quite different from the way that I have modeled the previous input and output resistances, where the input resistance of the basic amplifier was taken as Ri. So this is a quantity with respect to basic amplifier, okay, and Ro is again with respect to the basic amplifier. They are open loop impedances, whereas the RIF and ROF are basically the input and output impedances of a feedback amplifier. So please ensure that you are clear with these notations, and we will be adding few more notations further down the line, and ensure that you are clear with these two notations as of now. And I'm just going to call this as an ideal structure, except for the basic amplifier. Now, in this case, the feedback amplifier gain is written as the ratio of V naught divided by Vs, okay, whereas the open loop gain expression was defined as a ratio of V naught with respect to Vi, where Vi is nothing but the input voltage of the basic amplifier, whereas Vs is considered as the input voltage of the feedback amplifier. So these two are the two quantities that differs from each other, and one could use this model, ideal model, which I will not do it for you. You can just work it out, which could be written as something like A divided by 1 plus A beta. And this expression of this A divided by 1 plus A beta is same for whatever type of feedback amplifier that we are discussing. Either it can be a current amplifier, or even it can be a trans conductance or trans resistance amplifier. The definition of this closed loop gain expression always remains the same. Clear? Yeah. So one could actually bring down this configuration into a much simpler configuration as a two port configuration, which I will model it right now. And yeah, so this is just a simplified version of the same feedback amplifier, where the input is taken as Vs, and the input impedance seen by this voltage source Vs is taken as RIF. Okay. That is the input impedance, and we have a gain which is defined as AF times, which is nothing but the voltage gain of the feedback amplifier times that of the input source, which is Vs, into the ROF, okay, and we have this V naught being measured at the bottom. Okay. So this is a simplified version of the same network that we had here. Okay. So in this case, we have different components contributed from basic amplifier as well as the feedback network, whereas in the figure that has been shown is just an equivalent circuit model. Of the feedback voltage amplifier. Okay. And let me mark this as just the feedback voltage amplifier. Okay. And the one at the bottom is this. So now that we need to evaluate this RIF as well as ROF, and in order to do so, let us begin with RIF calculation, and let us see how one could do this. Okay. So as we know that the input, the input basically mixes a voltage. Okay. So by a series connection, we could write that the series mixing of Vf, okay, sorry, the series mixing of Vf generally reduces the value of Vi, right. Um, so it reduces the input voltage of the basic amplifier from Vs, okay. So basically the Vs is the one that goes to the basic amplifier, but because of the series addition, what happens is that this Vf will try to reduce this Vs from being directly applied onto this Vi, okay. So that is what I try to mean by this particular statement, and the way you can compute is by analyzing this. Through this particular analysis, one could write that the value of Vi when in comparison with respect to the source voltage Vs, one could write that it can be written down something like this, okay. So I would encourage you to check out this particular expression, how exactly you are getting this expression, but in a sense one could quickly see that uh, the input voltage to the basic amplifier, which is Vi, would be reduced by a factor from the voltage source Vs by this amount of feedback quantity, okay. So it gets reduced, and this is the quantity that actually tells you. So now because of this reduction, now in case if I just want to measure the input impedance, what I can do is that I can just ensure that the current flow through this particular circuit as labeled as just a second, I will just use some color. Yeah, I'll use the green one. So we know that the current that flows into the circuit is taken as II, and we also know that the ratio of this Vs with II will give us the input impedance of this feedback amplifier, which is RIF, okay. So with that, let us try to have a discussion, clear. So now I could write this II as a current flow in terms of Vi. So, so if I know the voltage drop across this resistance Ri, then I can evaluate the value of this II as Vi divided by the input impedance of the basic amplifier, which is Ri. And again, as I said earlier, the Vi value can be substituted from this expression, which, as I said, can be defined in terms of Vs divided by 1 plus A beta into the input impedance of the basic amplifier. And now the ratio of this Vs divided by II will define the value of this feedback input impedance of the amplifier, and based on which one could write that the value of this RIF becomes Ri, which is the open loop input impedance multiplied by the amount of feedback quantity, okay. So as you could able to see that the input impedance of the feedback network becomes higher by a quantity of 1 plus A beta. Is that is clear? Yeah. So this happens because of the series connection. So we'll just hold this relation that we have. Whenever we have a series connection, it results in an increase in the impedance value of the feedback network, okay, when compared to the open loop resistance, okay. So now let us try to look into the value of this ROF, and in order to have this ROF, uh, uh, we had already discussed that whenever we want to compute any output impedance, there are two things that we need to do. One is to kill the input source, right, and the second one is to apply Vx across the node at which we are trying to evaluate the impedance, okay. Yeah, so we are going to use these two equations in order to measure them. So in order to do so, let me just try to draw only the partial segment of this feedback network, or if possible I will just yeah, let me try to copy this network. I don't need this. Yeah. So I just have to perform the first task of killing the input source. So killing a voltage source Vs is nothing but making this short circuit here. So let me just use a short circuit in order to kill that input source. So I will do that, and after then I have to apply a Vx and measure the current flow Ix, right. So that the ratio of Vx by Ix will give us uh, the output impedance, which is ROF. Okay. So in this case, clearly what happens is that when I try to fix this value of Vx, uh, one could write that the value of, yeah, so again there is something that I have to pull out from the input quantity. So basically from the input loop I could see that the value of this, since because the value of Vs is right now killed, and we know that the value of Vs is always equal to the added version of Vi plus Vf, and right now this value of Vs has been shorted, and due to which we have this Vi is, is basically equal to minus of Vf. Okay. So we will use this result from here, and with respect to the output loop, again one could see that the value of this Ix could be returned as something like the current flow through this resistance R naught. Okay. So in order to write this current flow through the resistance R naught, we need to know what is the potential difference across this R naught impedance, right. So I am just going to use those potential difference value along with the resistance R naught in order to evaluate that. So towards the left side we have a voltage quantity which is mu times that of Vi, and towards the right side we have a voltage which is nothing but Vx. Okay. So let me write this Ix value as Vx minus mu times that of Vi, or this mu can be replaced with capital A. Okay. So let me write that in terms of capital A rather than mu, just because to avoid the confusions, because mu and A will carries the same meaning. So I'll just replace that with A itself. Okay. Yeah. So and divided by the resistance R naught will give us this particular quantity. And now one could write this feedback factor Vf as beta times that of V naught, right. So Vf is nothing but beta times that of V naught, and I am going to utilize that result onto our value of Vi. Okay. So beta is, sorry, Vf is nothing but beta times V naught, and due to which Vi will be returned as minus beta times that of V naught. So use this result and substitute onto the value of Vi over here. So and the V naught is basically is currently equal to Vx, so I can still replace them with Vx itself rather than writing it as Vx V naught. Okay. So based on this, when I try to plug in all these quantities, I will have Vx into 1 plus A times that of beta divided by R naught, and that gives us the value of Ix. So the feedback impedance ROF is defined as Vx by Ix, and due to which it becomes R naught divided by 1 plus A beta. Okay. So here clearly one could see that the output impedance R naught, which is the open loop output impedance, has got reduced by a factor of the amount of feedback quantity, okay, for a feedback amplifier output impedance. So the ROF value is defined by this. Okay. And we also know that whenever we, the type of connection that we have made across this output is basically a shunt connection. Okay. So this is our shunt connection that we have made, and whenever we have this shunt connection in general, the impedance will be reduced by this particular factor, whereas if the connection is a series, then whatever the impedance that we have as an open loop impedance will be raised by this factor of 1 plus a beta. Okay, so there are two conclusions that I can derive from here. One is if the feedback connection is a series, then the feedback impedance will be raised or increased by 1 plus a beta. Okay, whereas if the feedback connection is a shunt type of connection, then this feedback impedance, either at the input or output, whatever it is, in general will be reduced by a factor of 1 plus a beta, and these are the quantities that have been compared with respect to the impedances of the basic amplifier. Okay, so hope that it is clear. Yeah. So now that we'll just move on to the practical case where we try to have the non-ideal models for the sources, loads, as well as for the feedback network. Okay, and in order to model this non-ideal behavior of this feedback network, we have to choose a particular two-port parameter model, and we'll discuss about that as well. Okay, so let us go for the second case, which I call it as a practical case. And in this practical case, as I stated, the feedback network will not be an ideal voltage controlled voltage source, but rather it will be like a resistive network. Okay, resistive network, and these resistive networks, in short, load the basic amplifier. Okay, and when it loads these basic amplifiers, what happens is that what are the quantities that we have discussed, like the gain as well as the Ri as well as R naught. Okay, so each of these quantities, which are basically the components or the parameters that are associated with the basic amplifier, will get affected. Okay. So I think you are clear with this particular statement. And the next one is that we'll also consider the more practical conditions, like we'll also try to add the source signal impedances and the load impedances. Okay, we'll be considering those resistances as well. So when we add these two impedances, again all these three parameters of A, Ri and R naught of the basic amplifier will then get affected. Okay, so we'll just combine both these quantities and see how does it impacts our all these three parameters, and in turn we'll try to again revisit the voltage gain of the feedback network, as well as the input and output impedances of the feedback network, and we'll also try to define an extra parameter with respect to the input and output impedances as well. Okay, so let me try to model this. So if we draw a quick model where currently I will have the resistance Rs, which is the which tries to mimic the non-ideal model of the voltage source here, and then I'm not going to redraw this. We know that the non-ideal model of the basic amplifier. Okay, so I'll just put it in a box so that I will not waste time in redrawing those internal structures. And I will also include the non-ideal model of the load, which is nothing but a resistive load of RL, and the feedback network I will again put it in a box as of now, and later we will just use this replace these boxes of both basic amplifier as well as the um, feedback amplifiers or feedback networks with appropriate models in it. Okay. So as of now I just want to emphasize few parameters values. So as we know that the output of this is basically a V naught and of the basic amplifier, and that is the same that we would end up having across the load as well, and we will be sampling, or the feedback network will sample this output voltage V naught. Okay. And the output of this feedback network in turn gives us a voltage, feedback voltage, which is termed as Vf, and that would be connected in series with this basic amplifier, and the input of this basic amplifier will also be in terms of voltage. So let me complete this particular part. So now I have drawn this particular picture in order to demonstrate that how exactly we are going to measure the impedances values of the closed loop quantities. Okay. So now in this case, whatever the impedance that is seen by this voltage source is considered to be as RIF. Clear? Hope that it is clear from this perspective. So this is the same definition that I have explained before, and this RIF is nothing but the input impedance of the feedback network. And similarly, I would have the ROF, which includes even this load impedance RL. Okay, and along with these definitions of the feedback input and output impedances, I am going to introduce one more quantity, which I write it as Rin, which is quite different from Ri. So Ri is a quantity which defines the input impedance of the basic amplifier. Okay. So whereas this Rin is different from this Ri, so please ensure that. So in this case, this Rin, how it is different from Ri or this RIF is that this particular RIN will not include this source impedance into account. Okay, so that's the only thing. So it excludes the source resistance RS, and similarly, even here, I'm just going to add the R out. So again, this R out is a closed loop impedance, but the only thing is that it excludes the load impedance RL. Okay, so let me summarize all these three parameters in short. So Ri and R naught are basically the input and output impedance of the open loop or the basic amplifier, and we have this Rn and R out are basically the input and output impedance of the feedback amplifier, excluding let me write excluding Rs as well as RL. Okay. Whereas we have the last definition, which is the RIF and ROF. Okay. So these are again the input and output impedances of feedback network, but this includes the source resistance and the load resistance as well. Okay, and I'm just going to call this Rin and R out as the actual resistances or actual impedances, whereas I'm just going to call this RIF and ROF as the feedback impedances, and yeah, these are nothing but the open loop or the basic amplifier impedances. Okay, so clear, I guess you are clear with these definitions here, and later we'll just try to discuss with some set of problems here. Yeah. So now let us try to see which particular model can be used in order to model the non-ideal model of this feedback network. Okay, so we basically have, as I said, we have four uh, different type of two-port models. Okay, so two-port parameter network, which are H parameter, the second one being the Z, and the third one is Y, and fourth one is G. Okay, so these are the four different available two-port models that we have, and we have to choose a particular model that better suits this feedback network, where this feedback network samples in a voltage and then mixes a kind of voltage to the input source. Okay, so now among this four, it is only this H parameter that satisfies this particular condition. Okay, so in a way, the H parameter has can be modeled, okay, where at the input side of this or basically the output side of this feedback network, or let me write it as port 1. Okay, so in the case of port 1, what we have is H11, and we also have H12, and this H12 depends, like it's basically models our voltage controlled voltage source. Okay, and on the other hand, across the second port, we have one more parameter, which is H21, which has a transfer function of H21, but depends on the current flow of this I1. So I1 is nothing but the current that flows through this uh, first port. Clear? And we also have a resistance which is modeled as H22, or this H22 can be anything. Okay, so it is not just the resistance; it can be any type of network that it can fit here. Okay, so hope that this is the H parameter. And probably in the next class, I will discuss in more detail about all the different type of four-port parameter models, and then let me justify why a particular parameter model suits a particular type of feedback network. Okay, but as of now today, as the time goes on, I guess it is better to use this model as it is and then move on. Okay, and the voltage drop across this resistance path of H22 will give us this V2, and the current is modeled as I1 in this case. Okay, so this V2 is nothing but the drop across this H22 parameter. Now we will use this in terms of the feedback network. Okay, so I guess it is better to copy it again, the same model. Yeah. So in the place of this feedback network, I have to put in this H parameter model, and we are also going to assume some simplifications in this particular model. Yeah. So the H parameter will have this H11, and right now we will be replacing this H11 with R11 as the resistance, and we have a voltage controlled voltage source, which in this case was modeled as H12, and let me replace that with beta. So H12 is replaced with the factor of beta, or it's fine even if you have it as H12 is not a problem, and that would sense an input voltage where the input to the second port of the feedback network is a V naught. So let me write it as in terms of V naught, and over the other end what we have is a current controlled current source, and which is modeled as H21 times that of I1. Okay. So this is something that models the transfer function from port number 1 to 2. Okay. So it's something like a reverse transformation that uh, it is considered when we consider this H21 parameter. Okay. And along with it, we also have to model the non-ideal impedance of this second port of the beta network with the resistance, and I'm just going to model this resistance as R22 rather than writing it as H22. Okay, and the drop across this resistance is modeled as V naught. I hope that this entire picture is clear, and this entire thing models our beta network. Now, to this beta network, we will not consider this reverse transformation. That is, we will consider that there is no transformation happening from port number 1 to port number 2. So this has no transformation. So in order to have this no transformation from port 1 to 2, we have to have this H21 to be equal to 0. Clear? So normally we will just try to replace this H21 with an open circuit such that it pulls out the or it pulls out this transformation of 1 to 2 out of this particular circuit. Okay, so let me again copy this circuit and let me redraw the same circuit with so killing this H21 or a current controlled current source is by open circuiting that particular quantity. Clear? So this is what we have, and let me even draw this current, which is I1 throughout this. So whatever the current that flows out of this Vs is taken as II, and let me write this as well as an II quantity. Okay, the same current loops around through this and gets back here as II and then goes back to the circuit. Okay, so there is a loop of current flow through this basic amplifier as well as through the feedback amplifier or the feedback network. Clear? Yeah. So hope that this is clear, and we are ready to discuss about different quantities that we have mentioned here. So the very first thing is that the way that is being modeled is that we want to model how to say, like the next quantity that we really want to emphasize here is that we want to push all those non-ideal characteristics of the signal source, the load, as well as the feedback network. We want to remove all those non-idealities and push all those non-idealities to this basic amplifier. I want to push all the non-idealities, remove all those non-idealities, and push it to one particular structure, which is the basic amplifier, so that in the entire configuration I will have only the basic amplifier having all the non-idealities, and all other structures like input signal source, the load, as well as our basic amplifier will be completely taken as an ideal structure. So that what are the result that we have derived earlier in the first case, yeah, so what are the analysis that we have discussed in the first case, yeah, in the ideal case can be utilized for the discussion. Okay, so hope that I'm not confusing you people. The only thing is that I want to remove all the non-idealities from these sources and then push it onto this basic amplifier is what I just want to mention. Okay, now in this case let me try to push all these non-idealities to the basic amplifier. Okay, so the way that I can remove this non-ideality from this voltage source Vs is by removing this Vs Rs, okay, and pushing it towards the input side, okay. So I'm just going to shift this guy and ensures that this Rs appears along the path of my basic amplifier, okay. So now whatever I'm reading here as Vi is the quantity that I'm measuring after this node Rs, clear. And we also know that if this basic amplifier is a non-ideal one, even this basic amplifier will have a resistance Ri associated with it. And similarly, I also want to make this beta network or the feedback network as an ideal one by removing this non-ideal resistance R11 out of the circuit. So this could be done by moving this R11 to the input of this basic amplifier, okay. So I'm just going to remove that, and then I am just going to rewrite it as R11, okay. So the voltage difference between this node and this node of this source resistance Rs and the feedback resistance R11 is taken as the voltage Vi. Is that is clear? So hope that it is clear for you. And now that the network would then become a pure network, okay. So without the voltage source as well as the feedback network has become ideal with respect to the input side, okay. Now we have to do the same with respect to the output. So the way that I can do is to push first of all the load impedance towards the basic amplifier so that the load becomes an ideal one, which is the open circuit. So let me just move this load towards the input side, okay. So I'll have this load been pushed towards the input side, and I will call that as RL, and I'm just going to remove this R22, okay. So I want to remove this R22 in order to make this feedback network is ideal from the uh, port number 2 as well, okay. So in order to do that, I have to remove this R22 and then fix it across or in parallel with this RL, okay. So let me use this same color and let me use it as R22 here, okay. So now clearly we also know that the internal structure of this voltage amplifier will have some sort of voltage controlled voltage amplifier. So let me model that, and it has a gain times that of Vi. Currently we know that the Vi is measured with respect to the source resistance as well as with respect to the feedback resistance R11, but in short the voltage controlled voltage source will depend on only on the drop across this Ri. So due to which let me label that the drop across this resistance Ri as V1, okay, and the voltage controlled voltage source will depend only on this value of Vi, not on the value of V1 and not depends on the value of Vi, okay. So I will write it as V1 times that of the gain. Hope that it is clear. So it in the previous case we had A times that of Vi, and after the inclusion of the source resistance as well as the feedback resistance it no more depends on the value of Vi, but rather it depends only on the drop across the resistance Ri. And if I label this drop across the resistance Ri as V1, then the voltage controlled voltage source will be a quantity which is A times that of V1, not as A times that of Vi, clear. And this will also have the source impedance which is modeled as R0, and yeah. So now I just want to bring out the different expressions out of this. So the very first thing is that I also have to remove this just because we moved our R22 to the basic amplifier. So now that we have made sure that this basic amplifier is cluttered with all different type of impedances, and we have to recalculate all our input and output impedances of our basic amplifier. So we know that Ri is the one that, let me use this color, okay. So we know that this Ri is nothing but the input impedance of the basic amplifier, which is measured from this voltage component Vi, right. So due to which one could see that this Ra is nothing but it's a series connection of Rs, Ri and R11, right. So it is Rs, Ri and R11. So previously we had this Ri to be equal to Ri itself, but right now the value of the input impedance of this quantity has got changed. So I think we have to have a different notation. Let me rewrite it as RID just because of the confusions that you might have from this term. Okay, the actual input impedance of the basic amplifier. Okay. So in order to distinguish that from this quantity, I have just replaced this previous Ri that I had here with RID, okay, or a differential input impedance of the basic amplifier. Okay. So now currently this is the new quantity that I have for the basic amplifier input impedance, and similarly uh, let us look for the output impedance as well. Now as we know that whenever we try to measure the output impedance, we first have to kill the like we have to ensure that the value of V1 is being killed, and when that is being killed, obviously the voltage controlled voltage source will become 0. Okay, so that is what we mean by this killing. So when V1 goes to 0, then A times V1 will also go to 0. So having a voltage source being 0 can be represented by a short circuit. Okay, so which means that the R naught that we have here will be shorted. Okay, that is what I try to mean here. So in that case, one could see that this uh, again I have to rewrite the actual resistance with something else. So let me write it as Rho1. Okay, let me use this Rho1 as the internal output impedance of the basic amplifier, so that one could see that all these impedances of Rho1, RL as well as R22, all these resistances appears in parallel. Okay, just because of the short circuit that we have made onto this. Okay. Um, while killing this V1. So due to which let me write this expression, which is Rho1 in parallel with RL in parallel with R22. Okay. So now it becomes pretty simple for us to evaluate the RO like RIF as well as ROF. Okay. Now we know that the input basically forms a series connection. Okay, there is a series mixing that is happening across the or the series connection that is being made for mixing this voltage VF, right. So whenever we have the series connection at a particular port, then we know that this RIF will be increased by this quantity of Ri times that of 1 plus A beta, and this is purely based on the series connection that we discussed earlier, just because the input has a series connection, whereas the output basically has a shunt connection, and due to which the output impedance would be reduced by a factor of this 1 plus A beta. Okay. And now that we just want to extract the values of R out and R in, which is supposed to exclude, which is again the feedback impedances, but these feedback impedances should exclude the resistance of Rs. I think I have mixed the quantities here. Yeah. Should exclude the quantity of Rs from the RIF, and the R out should exclude the quantity of RL from the ROF. Okay. Now this becomes pretty straightforward. That is, from this quantity RIF, I have to remove the source resistance because of this series connection quantity, whereas in order to exclude the resistance RL from this quantity of ROF, one has to do a simple algebra of doing this. Okay, so this particular formula will give us this quantity of R out. Okay, so so let me end this session because the session is going very long, and Yeah, there is one more thing that I just want to complete just before ending this session. We also have to identify the factor beta whenever we want to calculate this uh, closed loop gain. So I'll just talk about this uh, beta calculation, okay, uh, just by taking this model of H parameter. Okay, so let me quickly do this. Yeah, there are a lot many things I have to discuss. Uh, Let me discuss with the question of R11 and R22 as well as the beta. Okay, so I will use this model. Uh, so the input is basically a current, which is II. Let me use it as II, and this is my H parameter. And across the output, what we have is a kind of current controlled current source, and which could be written as H21 times that of II, and it also has a resistance R22. Okay, so in the previous case, I just said like we are just moving them the value of this R11 and R22 towards the basic amplifier, but in order to do so, first of all we have to remove this R11 quantity away from this from this voltage controlled current source, as well as away from the current controlled current sources, right. So there are certain conditions that has to be applied in order to do so. Now in the case while trying to extract the value of this R11, we basically want this voltage component. Let me fill the other quantities as well so that it becomes clear. Yeah. So in order to extract this quantity of R11 out of this network, we have to basically kill this voltage controlled current source, which is beta times that of V2. Now killing this means that I need to make this V2 to go to 0, right. So if I could do so, then this component of voltage controlled current source will become automatically short circuited, and that is how I can extract the value of this R11. So in order to do so, I first of all have to take this feedback network and make this V2 to go to 0. So that could be done by making the short circuit at port number 2. Okay, and whatever that I am just calculating as an impedance will give us the value of this R11. Hope that it is clear. And the next one is the computation of this this R22 quantity. Now in order to calculate this R22 quantity out of the second port, we have to kill this current controlled current source, right. So in order to kill that, I have to ensure that this I1 has to go to 0. Okay, the input current I1 has to go to 0, and the way that it can be done is by open circuiting. So whenever we have an open circuit in a particular path, then there won't be any current flow through this particular port, right. So clearly, while computing the value of this R22, we want to have an open circuit condition at the second or across the first port, such that I can evaluate the impedance of R22, and the normal procedure of calculating the impedance remains the same. So which is basically apply Vx and measure Ix, so that the ratio of Vx by Ix will give us the resistance. Okay, so that applies for both these calculations as well. Okay, so having done all these things, the one parameter that is ending that yet to be computed is the factor of beta. Now that in order to calculate this factor of beta, we are going to utilize just a second. Yeah. So we are just going to utilize the feedback network. Now in this feedback network, the consideration is that this H21 current source is neglected. Okay, so which means that this is made as a 0, and with that kind of network we will be utilizing. Even here, even though it is neglected, we are using those concepts in order to check whether we have to open circuit or close circuit it. Okay, So that is the condition that we are using these components or these controlled current sources or controlled voltage sources for the discussion in order to ensure while calculating this R11 and R22 what type of connection has to be made across the other end of the port. Okay, only for such discussion we have included this H21 and this beta or H12 parameters, otherwise there is no need of these inclusions. Okay, so in this case we know that the feedback factor is basically defined, and the input to this feedback network is basically a V naught, and the output of this feedback network is just a voltage for a voltage mixing and voltage sampling feedback network. Okay, so it is defined as V naught by Vf quantity, and the way that it can be done is by applying some sort of voltage towards the input and measuring the voltage across the second port. Okay, so apply some voltage source towards the input port and measure the output port voltage. So that it's a pretty simple quantity, and I can write it as, sorry, beta is Vf divided by V naught, because the input is this is my input port. Okay, and the input is basically V naught and the output port has this voltage Vf, okay, and under the condition that the value of I1 is equal to 0. Okay, so so again let me draw this final circuit, which is the open loop or the basic amplifier circuit, which could be used to compute this Ri and R naught. Okay, so we know that this basic amplifier circuit will have an input voltage, and along with this source resistance and this R11 parameter from the taken out from the feedback network, and it will also include this feedback network output component as well as RL. Okay. So now the measurement of these impedances are labeled as Ri and R naught. Okay, so it's just the same thing that I discussed earlier. The only thing is that I have just given a basic or an equivalent circuit model for this. Okay, so it's the same discussion that we had it while we discuss about this input impedance Ri and the output impedance R naught in this case. Clear? So with this I will end the session, and let me just come to Zoom so that if you have any doubts we can have a discussion on it. Thank you.